let's go through how to do a titration problem for a redox equation. The equation that we have here has already been balanced for acidic conditions. Now, once having it balanced for acidic conditions, what we need to do is find out, with our given information, how many moles of reactant we have and how many moles we need to react with that. The information we're given is we have 0.100 molar Ce4 plus ions. Now, the capital M stands for moles per liter. That's a measure of concentration. We can use this in a proportion to find out how many moles we have of Ce4 plus in the 10 milliliter sample that we're going to use in the problem. The 0.100 molar, or moles per liter, we can set up in a proportion where we have 0.100 moles of Ce4 plus ions per 1 liter of solution. If we know we have 0.1 moles of Ce4 plus in 1 liter, we can then solve for X moles of Ce4 plus that would be available in our 0.01 liter sample of solution, which is the same as 10 milliliters. Solving for X gives us 0.0010 moles of Ce4 plus ions. This is what we're going to work with in the problem to figure out how much alcohol is present in the blood of the sample subject. So at this point, what we know is that we have a sample with 0.0010 moles of Ce4 plus ions. We also know from our balanced equation that the alcohol and the Ce4 plus react in a 1:12 ratio. This allows us to set up another proportion to figure out how many moles of alcohol will react with the moles of Ce4 plus that we have present. The balanced equation gives us our known ratio that we have for the alcohol and Ce4 plus ions. The equation tells us that one alcohol molecule will react with 12 Ce4 pluses. We don't have 12 Ce4 pluses, we have 0.0010 Ce4 pluses. That'll react with X moles of C2H5OH. Solving for X, we find that we have 8.33 times 10 to the negative fifth moles of alcohol, C2H5OH, are going to react with the moles of Ce4 plus that we have, the 0.0010 moles of Ce4 plus. Now, what we just figured is that we have 8.33 times 10 to the minus 5 moles of alcohol. Now, the alcohol is contained in a 5 milliliter sample of blood of our test subject. We want to find out what's the concentration of the alcohol in the blood. Now, concentration, again, is a measure of how many moles there are per liter. That's our unit of measure for concentration. To calculate this, we need to know two things: the number of moles and the number of liters. We have our moles, and we also have our number of liters. This will allow us to calculate the concentration using a proportion. The information we have so far are number of moles of alcohol and our volume of alcohol, the 5 milliliters, which is converted to liters, 0.005 liters. We know we have 8.33 times 10 to the negative fifth moles of alcohol present in our 5 milliliter or 0.005 liter sample of blood. This would be the same as, in a proportion, X moles of alcohol present in 1 liter of solution. Once we have it in terms of moles per liter, this would be our concentration or molarity of the alcohol in the blood. Solving for X gives us that we have 0.0167 moles of alcohol present in our 1 liter sample. This gives us a concentration of the alcohol of 0.0167 moles per 1 liter, which can also be written as 0.0167 capital M, which stands for moles per liter or molarity. That's the concentration of the alcohol in the sample of blood. What we now need to do is compare what we found for the molarity of our alcohol in the blood to what is considered legally intoxicated. We see that this is going to be less than 0.0176 molar alcohol in blood, the cutoff for what determines if someone is legally intoxicated. So in this case, the response would be no, this person is not considered legally intoxicated with this level of alcohol in their blood. Now, let's try the second problem from the practice set done in class on Tuesday, November 22nd. In this problem, this is already balanced for basic conditions. And we're given that we have 0.250 molar sodium hydroxide. We want to find out how much sodium hydroxide is necessary to completely react with 2.50 grams of zinc. Our first course of action is we want to find out how many moles of zinc do we have present in our 2.50 gram sample. From the periodic table, we can find that 1 mole of zinc has a mass of 65.38 grams. This allows us to begin setting up a ratio and a proportion that we can use to find out how many moles are present in our 2.50 gram sample of zinc. If we know that we have 1 mole of zinc present in 65.38 grams of zinc, we can now solve for X moles of zinc that would be present in 2.50 grams of zinc using this proportion. When we solve for X, it gives us 0.0382 moles of zinc are present in our 2.50 gram sample of zinc. If we now take a look at the balanced equation, we can see that for every 7 OHs that react, they react with 4 zincs. This will allow us to set up a proportion to figure out how much hydroxide would be necessary to react completely with our 0.0382 moles of zinc that we have present. We can set up a known ratio from the balanced equation, which tells us that we have 7 OHs per every 4 zincs. Using the known ratio of 7 OHs to 4 zincs, we can solve for X OHs that will react with 0.0382 moles of zinc. Solving for X gives us 0.0669 moles of hydroxide, which is how many moles of hydroxide we'd need to completely react with the 0.0382 moles of zinc that are present in our 2.50 gram sample of zinc. Now our concentration of sodium hydroxide is 0.250 molar. The capital M stands for molar or moles per liter. This allows us to set up another proportion. The 0.250 molar known solution that we're given tells us that we have 0.250 moles of hydroxide ions per 1 liter of solution. This we can now use in a proportion, knowing that we have 0.250 moles of hydroxide per 1 liter, and that our sample that we have requires the use of 0.0669 moles of hydroxide to react with our zinc. We can now figure out how many liters of our hydroxide solution will contain the needed 0.0669 moles of hydroxide. Solving for X gives us 0.268 liters, which would be 268 milliliters of 0.250 molar NaOH will provide us with the needed amount of hydroxide ions to completely react with our 2.50 gram sample of zinc.